Started with another Coffee Shop Astrophysics talk. Thank you all for being here today as we start a new semester, the fall semester for UWM, and a new semester of Coffee Shop Astrophysics with 4 great presentations that we have planned out for you September, October, November, December. If you don't already know, you can keep up with all of our events either on our social media, Facebook, Instagram. We do record all of these talks and then upload them to YouTube afterwards, where you're able to view them there. Or if you know people who are not able to attend these talks in person, obviously you can then point them to the YouTube channel where they can watch these recordings at any time. Also, you can check out our website, where we have all of the up-to-date information about the talks, the talk topics, the talk speakers, and when they are going to be given. All you have to do is Google Coffee Shop Astrophysics. We have a unique enough name that we really have no competition whatsoever on the first page of Google search results. So that's really all you have to do. Anyways, if you do have an idea for a future coffee shop talk, I mean, we've been doing this for 10 plus years now, Coffee Shop Astrophysics, but there's still so many things that we could talk about that we haven't talked about, maybe that you would like us to talk about. And if you have such an idea, you can let us know either by coming up after any one of these particular talks, just chatting with us, or you can visit our website where we have a form that you can fill out with any ideas that you might have. Anyways, I'd also want to point out that we are not the only astronomy or astrophysics related public outreach group in the state of Wisconsin. We do have our wonderful friends at UW-Madison Astronomy on Tap who do similar, more or less similar types of talks in Madison. They have one coming up on October 15th from 7 to 8:30. If you happen to be out there at that time, be sure to check it out. They have very fun events. If you miss this one, they actually have another event on October 26th, and that's going to be here at 1 p.m. as we invite them back for a special joint Coffee Shop Astrophysics and Astronomy on Tap presentation. So who are we? Coffee Shop Astrophysics is a group of postdocs, graduate students at the University of Wisconsin-Milwaukee in the Center for Gravitation, Cosmology, and Astrophysics. Here's all of our lovely faces up there. And today's speakers, we have 3 of them. I am not one of them. I'll be passing this mic over. Our 3 speakers are Kumar, Sarah, and Shashwat, and they'll be talking about galaxies. And with that, I'll hand it over to our first speaker.
Right, hi everyone. Can you guys hear me? I'm Kumar. I'm a graduate student here at University of Wisconsin-Milwaukee. I'm going to talk about the origin of galaxies, how we got from the Big Bang all the way to galaxies that we know today. First, what are galaxies? Well, galaxies are massive systems, and they have stars, they have gas, they have dust, and all held together by gravity with a lot of dark matter within the systems. The galaxies were first the observations of what we know today as galaxies happened back in the 17th and 18th century. This happened soon after the telescopes were first invented. Galileo and Messier, they all looked up at the sky and noticed fuzzy objects in the sky. At the time, they called these fuzzy objects nebulae. And in the night sky, you can kind of see these fuzzy objects even today, but you might need a telescope or a long exposure photography for seeing it. And later in the 1920s, Edmund Hubble studied these fuzzy Andromeda in a little bit more detail, and he noticed that these things had little stars in them. These systems we now know as galaxies. And this marked the beginning of modern extragalactic astronomy. Today, we have a wide range of telescopes. We have ground-based telescopes, like the one on the left, which is the WM Keck telescope in Hawaii. We also have space-based telescopes, like the Hubble Space Telescope and the recently launched JWST. With these telescopes, we collect a lot of spectrographic data, and then we analyze them as scientists, and then that's how we learn more and more about the universe as we know today. Studying all this, we were able to kind of infer what happened from the Big Bang to what we know today in the universe. So just after the Big Bang, the universe was really hot, it was dense, and it was really small too. It was so dense that particles of light or photons just kept bouncing between these ions in the dense medium, and it was never able to escape. So it got trapped there. But after the Big Bang, the universe started expanding, and subsequently its temperature dropped. So as the universe expanded, the light that was trapped in the dense clump before was now able to escape. And this was the first time the universe had light. We still see this light today as a really faint cosmic microwave background. This whole thing happened just 380,000 years after the Big Bang. So once the universe expanded, well, the temperature dropped and the whole thing cooled down. This meant that the ions in the universe was able to recombine and form atoms. This process is called a recombination, but the consequence was these don't produce light. They're just neutral atoms. So the universe entered its dark ages. There was no more light again. So this was from the time of CMB, which was the cosmic microwave background at 380,000 years, till about 100 to 200 million years after the Big Bang. During this dark ages, the universe is mostly made up of neutral hydrogen and helium. And there were slight density fluctuations in the universe during this time, which caused this gas to collapse under its own gravity. And this is expected, or this is the process that led to the formation of the first stars in the universe. So the first stars, again, this is the time the universe saw light again after the dark ages for millions of years. And again, the universe didn't have any elements other than the lightest ones like hydrogen and helium. So these stars were made up of hydrogen and helium, and they're expected to be massive and short-lived. And these were the stars that first created heavier elements that are heavier than hydrogen and helium, like oxygen, nitrogen, and so on, through a process of nuclear fusion in its core, and the process we call nucleosynthesis. The stars didn't live for too long, but they died spectacularly in a supernova explosion. And unfortunately, we haven't had any direct observations of these stars yet. But we know its existence through observations of stars well close to us in the local universe, and also stars that are further away, close to the, I guess, 3 billion years after the Big Bang. So studies of all these stars let us extrapolate the data and infer that the first stars had a similar composition. The stars we know today are called population 1 stars, the stars like our sun. A little further ago, the stars had lesser amounts of heavier elements in them, and these stars were population 2 stars. And the first stars that were just hydrogen and helium we call them population 3 stars. The numbers are just a classification based on how much heavy elements are there in the star. So compared to the stars we know today, compared to the stars we know today, like the sun up here, the first generation star is expected to be massive. It's about 300 or so times bigger than the sun. Before we talk a little bit more about population 3 stars, it's important to highlight what role dark matter plays in the formation of the first stars and galaxies. Dark matter is something that does not interact with light, but it only interacts through gravity. Everything we know and see, well, we're able to know and see because it interacts through light. Dark matter is not one of them. It only interacts through gravity, and it helped collapse these gas clumps in the universe to form um, to form the first stars and the first galaxies. Without the dark matter clumps in the universe, normal matter would not have collapsed as soon as it did. It needed some assistance from something that's a little bit more gravitationally available. Dark matter, again, since we don't see it or it doesn't interact with light, we only know its existence through different observations. For example, in the image you see here, you see distortions around the little dots. These distortions are just galaxies, but the light from it is warped because of the presence of something in front of it that is massive. Normal matter would not cause distortions like this. There has to be some other object there or some other matter there that's causing this phenomenon, and we'd call that dark matter. So back to population 3 stars, or the first stars. As mentioned, these died in a massive supernova explosion, and this supernova explosion scattered the heavier elements that it created in its core all across the universe. And, side note, we as astronomers call everything other than hydrogen and helium as metals. It just means that it's heavier than hydrogen and helium, or the primordial elements. So population 3 stars scattered these metals all across the universe, and it got mixed with all the gases and everything that were around. And these metals allowed these gas to cool more efficiently. So the cooling process is essentially, there is a clump of gas that wants to collapse because of the gravitational forces, but the gas itself is hot, and heat is just the thermal motion or that causes the particles to move really fast. This creates pressure, and the pressure tries to push out. So it's a constant battle between gravity trying to squish it down and the thermal pressure trying to stop it from collapsing. But when metals were introduced in this gas, metals were able to absorb and radiate this energy out of the gas, which meant cooling was more efficient, and collapse happened much more easily because of gravity. So, following what happened after the first stars, so population 3 stars, they produced heavier elements, or what we call metals. The population 3 stars then died in a supernova and scattered all these metals or heavier elements into the gas around gas in the universe. Metal-rich gas meant more cooling or more efficient cooling, and that created less thermal pressure in clouds, which meant the gas clouds could now collapse more easily. And this created the first galaxies, or what we call the proto-galaxies. So proto-galaxies, or the first galaxies, did not have a defined shape like we see in galaxies today. They were irregular, they were small, and they were also spaced much closer than galaxies today. This is a consequence of expanding universe. So the universe as we know it expands at an accelerated rate, but we're talking a long time ago, so it wasn't as big as it is today. That means in proximity, all these galaxies were closer together, which meant that they could interact with each other gravitationally, which meant that they could merge, they could collide, they could gravitationally pull one another and create larger structures in the universe. So this merging process was not, well, it's a very violent process. There are stars, there is gas in these galaxies, and well, the stars are small compared to the size of these galaxies. The stars usually don't collide, but the gases do. And once gases collide, the density in that region goes up, which means there is more gravitational interactions in the gas, which leads to collapse and the formation of new stars. And every time there was a merger, it triggered star formation. There was a bunch of stars forming during these collisions. Once stars form, it interacts with other stars gravitationally, so it's a whole process of mergers gravitationally pulling other stars and creating structures slowly. This animation kind of shows how all that works, but in a really accelerated rate. Obviously, it does not happen this fast. It happens over the span of millions of years. But essentially, you can see how these proto-galaxies in the early universe merged with one another and created other systems which are larger and closer in appearance to the galaxies we know today. Sarah will now talk about galaxies in general, its properties, and how it compares in size to other systems in the universe. So please welcome Sarah.
Hi. So before I start talking what I want to talk, I just want to discuss how big our galaxies are. Because we know we talk about galaxies, but it's nice to really know what are their size in terms of stars or the Milky Way, but also in terms of the universe. So my first thing is how big is our Milky Way? And it's pretty big. Its diameter is almost 90,000 light years. And the light year is the time it's the distance that the light travels in 1 year. So even the light, that is the fastest thing we have, would take 90,000 years to cross the Milky Way from one side to the other. Also, the mass of the Milky Way is estimated to be around 1 trillion suns. So it's a lot of mass. But most of this mass is not on normal matter, the matter that we can see, for example, on stars or gas, but it's on dark matter. So Kumar talked about a little of dark matter, and we do see that dark matter is the most predominant matter in our Milky Way and in the galaxy as a whole. But if you think about the other part of matter, the ones that we actually can see, the rest of this mass is mostly on stars. So stars makes, the mass of stars in our Milky Way is estimated to be 50 billion suns. And we also have a lot of gas, which has a mass of around 1 billion suns. And we have a massive black hole that probably we've heard about before in the center of our star. So you may ask, how much of this mass of this massive black hole corresponds to the mass of our Milky Way? And it's not a lot, because even though it's massive, it's only 4 million suns, so 4.3 million suns. So stars and gas is in the billion part, and the massive black hole is in the million. So it's massive, but not as massive compared to the mass of all stars that we have in our galaxy. But we can also think that our Milky Way is really small compared to the whole universe. So what I have here is our local supercluster, known as Laniakea. Its diameter is 500 million light years. So even light would take 500 million years to cross this whole structure. And the mass of this whole supercluster is 100,000 galaxies, like ours. So it's much bigger than our Milky Way. And this is not even the observable universe. Because if you think about the observable universe, its diameter is around 93 billion light years, and the mass is around 100 billion Milky Ways. So it's huge. There's a lot of galaxies in the universe, and ours is just one of them. So the estimate says that we have around hundreds of billions to 1 trillion galaxies in our observable universe. Of course, we don't know all of them. We probably know something in the order of millions, maybe almost 10 of millions of galaxies. But there's still a lot to be known, but we do have a lot of galaxies that we already do. So for the ones that we know, what we know about them? One thing we know is that they come in different shapes. So the three main shapes we have is spiral, elliptical, and irregular galaxies. The most common one are the spiral galaxies, like our Milky Way. Here we have a few more, but we also know that they come in different sizes. So here our Milky Way is the biggest one. In this case, the galaxies are on scale. But if you think about other galaxies, we see that our Milky Way is not the biggest one, actually. The Milky Way is here, and the previous slide is this little thing here. So we see that there are galaxies that we can't even see anymore individually, and there are other ones that are much bigger than the previous slide as a whole, like M87. So galaxies can come in the most different shapes. And now I want to talk a little bit more about the different types of galaxies we have. And the first one that I want to talk about is the spiral galaxies. Spiral galaxies like our Milky Way, and is the most common type of galaxies we see out there. So we see how they were formed. Kumar told us that it's like a lot of small, irregular galaxies that merge together to form a bigger one. This is how spiral galaxies are formed. But then we may ask, how do they get the disk? Because what we think about spiral galaxies is that they have this nice disk with the spiral arms, but if you look them edge on, like in this picture here, you will see that they look like a pancake. They are like flat and round. And the reason why the disk is formed is because of something called angular momentum. So if you don't remember what angular momentum is, I put this picture here that maybe will ring some bells from physics classes. Angular momentum is the thing that is conserved when we have like a ballerina doing like the pirouettes or a figure skating doing a jump. And it's like in the case of the jump, for example, we see that the figure skater closes her arms so the angular momentum is conserved and she can rotate a little faster. So this is the same reason. So if you imagine in a galaxy, what will happen in the beginning is just like this chunk of gas, each gas rotating in a different plane in a different direction related to the center of the galaxy. But if you wait long enough and let the gas particles of the gas collide with one another, what we'll see is that there's a plane in the direction that there's more particles rotating than the others. And with those collisions, the other directions will cancel each other, and the only direction we'll have is the direction and the plane that has more gas particles rotating related to the plane than the others. This is also the reason why the solar system is a plane. All the planets rotate in the same plane. And the other nice thing about spiral galaxies is that they have a lot of what we call star nurseries, places where new stars are being created. Those are molecular gas clouds, and here we have some on the Milky Way, some pictures. So for example, this one is very famous. This is the Hubble picture of the pillars of creation. We also already have a JWST picture of this, and this is where new stars are born. But if you are looking at a galaxy far away, you'll see those star nurseries because there's like those very bright blue-violet dots. Those are the places where stars are created if you look at distant galaxies. And now that we talked about spiral galaxies, I want to go to elliptical galaxies. And the first thing I want to talk about is how they are formed, because the previous idea that small galaxies merge together to form a bigger galaxy is true for spiral galaxies, but not for elliptical. So on elliptical galaxies, what we see is that we will have two big spiral galaxies merging with one another. So here, oh, what happened? I'm really sorry for that. So what we see here first is the simulation, and on the other side, in here, what is? I'm sorry for that. Technical issues. Okay, hopefully it worked this time. So here, what we have are real photos from NASA of galaxies merging. So those two here are galaxies merging. So here we see that they are a little far away, and then here the two galaxies are closer. So those are not the same galaxies because this happened in the time scale of hundreds of millions to billions of years. But we can see like galaxies that are a little further apart and then a little closer. And this is the two galaxies that have already merged and have an elliptical galaxy. So this is the elliptical galaxies that we see. And in the other side, we have a simulation of how this happened. And we see that it's a very violent process. So what happens during this process is that the disk that we had before, each one of them is in a different direction. The merge is very violent. The disk is disturbed. We don't have a disk anymore. And what happened during this merger is also that a lot of gas is expelled from the galaxies. So in the end, we have a galaxy that there's not a lot of gas. So if there's not a lot of gas, we see that gas is the place where new stars are born. There's no new stars, not a lot at least, new stars in these galaxies, because we don't have gas anymore. And if there's no gas, there's no disk. So when the stars, like the merge finishes, everything is symmetrical again, the shape we see is more like an egg. So you can see like the other galaxies is round, this only one is also round. So the difference is more like when you think about the 3D perspective, because spiral galaxies are pancakes, elliptical galaxies are eggs. So they have like this 3D shape that we don't see on the other type of galaxies. And they can also be huge. So if you imagine that we are like merging two big galaxies together, they will be even bigger. So the biggest galaxies we know in the universe are actually elliptical galaxies. And just one fun fact here, it's M87, which it's one of the big elliptical galaxies we have, is also the galaxy that had the first picture of the black hole that Shashwat will talk more about it. I just wanted to point and make this connection. And the last type we have are irregular galaxies. We've seen one way of forming them before, which is like when the merge is happening, but they haven't finished yet. So we have this weird blob that are our galaxies merging. But there's another way, because if we have a small galaxy in the outskirts of our spiral galaxy, for example, the Magellanic Clouds in our Milky Way, that it's a satellite dwarf galaxy right outside of the Milky Way, the gravitational pull that the Milky Way does on this galaxy distorts its shape. So this is another way that we can create irregular galaxies. And since we talk about mergers, I just wanted to do a rule of thumb, because in the end, all galaxies are formed via mergers. If we have a spiral galaxy merging with a small galaxy, we'll have a bigger spiral galaxy. But if you have two big spiral galaxies merging together, the final product will be an elliptical galaxy. So the last thing I want to talk about is how galaxies were back in the past. Because we had Hubble, now we have JWST, and we know how they evolved over time. So if you look farther back enough in time, what we'll see is that the galaxies were a little smaller, and the spiral arms were still like taking shape. So we see that if you go back in time, they are smaller and smaller, and the spiral arms are sometimes less pronounced than they are now. And the nice thing is that even that far away, we can still can see the very bright blue regions of star-forming regions. So I think this is nice. And another thing that you may realize is that if you go further back in time, they are a little more red. If you have been to some of our talks before, maybe you know the reason, but I have to say, the reason is because there's something called cosmological redshift. So as Kumar said, our universe is expanding, so everything that is in the universe expands with it. And the light that was emitted by a galaxy like tens of billions of years ago also expanded and stretched. So if a galaxy emitted a light that is very short, now we will see it much stretched. And this actually says that if the light was emitted in a blue region, now it's red. Blue has a shorter wavelength, and red has a wider wavelength. And this is one of the reasons why James Webb is so important to see the very first galaxies. Because not only JWST has a larger mirror compared to Hubble, but also it is an infrared telescope. Hubble is an optical telescope. There's a range that the two overlap, but they function in different regions of the electromagnetic spectrum. So JWST is better to reach those very red galaxies that we have in the beginning of the universe. So just to finish my part, I just wanted to say a little bit of what JWST have found out, because it's not there a long time ago. We don't know a lot of it yet. Data is still being observed, being analyzed. So what I'm saying is more like initial discoveries. But I think it's important to say. So back in last year, we saw news like those saying that the galaxies, very early galaxies, were a little bigger than we expect. And we see that they actually get a little more matter over time, a little more matter over time from like those small galaxies. And what people was seeing is that it seems that they were a little bigger, but this is not true. They reanalyzed the data, they got more data, and what they found is that they are actually the very perfect acceptable size. So that's the reason why we have to be a little careful when we see those news about JWST, because there's a lot of things that are still being observed, data being analyzed by different groups, so things can change over time. And one final thing I want to say is the shapes of those very early galaxies that we have seen by JWST. And one thing that they are finding is that if you go further back in time enough, they're even flatter than the ones that we see today. So what they say is that our Milky Way probably have what they call a surfboard shape. And the difference between this and what we have right now is that it's even flatter than they are right now. So if using the pancake analogy now, we can imagine that back in the day, not only the Milky Way wasn't that round, it was more like on a surfboard shape, but also in terms of height, it was more like a crepe, a French crepe instead of a pancake. So we see that those shapes that I've just said, like spiral, elliptical, regular galaxies, are something that we observe a little closer to us. If you go a lot back in time to the beginning, when they were still formed, what we see is that the shapes are a little different. So with this, I finish my part, and I pass to Shashwat.
Hey everyone, can everyone hear me fine? Okay. Yeah, so thank you, Sarah and Kumar. I'll be talking about black holes that lurk in the centers of galaxies, as well as a little more on mergers and the future of galaxies, or what happens to them after everything we've discussed. So to start off with, Sarah mentioned that at the center of our Milky Way galaxy, there is a massive black hole, in fact, a supermassive black hole, and it's called Sagittarius A star. This is an updated picture from the Event Horizon Telescope collaboration. They took this and now they've reanalyzed the data so you can see much more detail. This is called Sagittarius A star because it's in the direction of the constellation Sagittarius. And as Sarah said, it's 4 million suns worth of mass. And the reason we know what the mass is because way back, scientists were able to see stars moving at ridiculous speeds around something that was seemingly invisible. And so by looking at the orbits of these stars, we were able to tell that there's something around 4 million solar masses big lurking in there. And our black hole is relatively quiet, but some of these can actually be a lot more active and be feeding on stars and gas, and we call these active galactic nuclei. So to take an example of, to take a look at some of these monsters that are way bigger than our own black hole, M87 star, again, thanks Sarah for bringing that up, was the first picture taken by the Event Horizon Telescope, and this is a black hole that is 2.4 billion solar masses big. So it's around 1,000 times bigger than our own black hole. But that's not even the biggest one, because there's this black hole called TUN 618, which is 40.7 billion solar masses. So around 10,000 times the mass of our own galaxy, our own black hole. And this is probably one of the biggest black holes that we've seen. So let's take a look at what happens when these black holes actually feed on stars and dust and gas. So what happens is the matter starts spiraling into the black hole. Here you can see this black region is the event horizon, the point at which there's no return. Once matter crosses the event horizon, there's no coming back, not even for light. So as this matter starts spinning around the disk, because of the gravitational forces, some of this matter spins at close to the speed of light, and it builds up friction and it begins to glow. And so you get very energetic gases and plasma around this black hole. In fact, it can build up to the point where the black hole is almost eating too much, and it ends up shooting out in these relativistic jets from either poles of the black hole. And this is an extremely energetic event. So the disk is giving off X-rays and gamma rays. So if you remember the scene in Interstellar where they're flying past Gargantua, they would not have survived. It would have been a really bad experience. So, and some of these can get really, really energetic, such as M87 star, which is a pretty big black hole that's been feeding and is very active. So these active galactic nuclei are so luminous that when we first saw them, we weren't sure what they were, and we referred to them as quasi-stellar objects. And that name has stuck, and they're called quasars now. And they emit so much light, just like these beams that, oh, sorry about that. Yeah, just like these beams that shoot out, you can see them, and they are hundreds of thousands of light years long. And these are some of the most luminous objects in the entire universe. They can outshine entire galaxies, and they're really useful because they're so bright and we can see them from really far away in the universe. We can use them to study the universe and what lies between us and these extremely bright objects. So these are called quasars, and if you happen to have one that's actually facing you, where the beam is headed right for you, that's a bad situation, but those are called blazars, just because we need a new category for something this destructive. So what is the function of these supermassive black holes? That's the SMBH. It's not fully understood how what role they play in the formation of galaxies. They are extremely massive, and they sit in the centers, so they probably play a vital role in the formation of galaxies and protogalaxies, as Kumar was mentioning. But we know that they also play a role in the death of galaxies. So here's an example of an active galactic nuclei called Cygnus A star. And that's the galaxy right there in the middle, and these are the jets it's shot out from this black hole. So as the black hole feeds and shoots out gases and plasma, the galaxy has less and less gas and viable fuel for star formation. And so eventually this stops the galaxy from producing any more new stars, killing the galaxy essentially. So some of this gas may fall back down into the galaxy, but some of it is traveling so fast that it's gone and will never fall back in. So the Milky Way, like I said, our black hole is pretty quiet, but there is evidence that at one point it was active. There are these structures called Fermi bubbles where we see X-rays and gamma rays emanating from the center. So you can imagine that there used to be jets that shot out. And this is about almost more than half the length of the Milky Way, the diameter of the Milky Way long. So at one point, Sagittarius A star was also feeding on stars, and who knows, maybe in a few thousand, 10,000 years, it'll start feeding once again. So just a small note on mergers, as Kumar and Sarah have already gone over this. Galaxies are drawn towards each other because of their gravity if they're close enough, and they can merge. And it's likely that from the very first proto-galaxies, most major galaxies that we see today emerged from a hierarchical formation of mergers. One example right here is these two galaxies colliding. And as Kumar mentioned, you get a lot of star formation because the gases collide. So here's a famous example called the bullet cluster, where these two parts of star clusters pass right through each other. So the red is the normal gas and matter, and the blue emphasizes the dark matter around these things. So the dark matter can just pass right through, but the gases will collide and hit each other. And so when these gases come in close contact, you get regions of overdensity that then collapse to form stars. So merging galaxies can actually trigger new stars to form, and sometimes this merger rate can be as big as 1,000 sun-like stars per year. And once again, I know Kumar mentioned this, but just so you all feel calm, stars do not actually collide head-on when two galaxies merge. There's enough space between stars that they just pass through each other. We'll do questions at the end. Yeah, thanks. So yeah, the stars on average are 4-point-something light years apart, and so there's enough room that stars never actually end up colliding head-on, just the gases. And so what happens to these black holes when galaxies merge? Well, they end up forming binaries where if they come close enough, they start orbiting each other, and they actually release gravitational waves. If you remember our talk that we did last semester on the gravitational wave background, this is the result that we expect from all of these merged galaxies together. So all of these really massive black holes orbiting each other, giving off gravitational waves, and slowly moving closer and closer until they merge. So this is happening all across the universe from all these galaxies that have merged. But there's still an interesting process here because we don't know how they get to this point to be close enough. You can see after they merge, the black holes need to get close together enough, but if we just leave them up to their own devices, this process could take longer than the age of the universe. So something else needs to be going on here. Maybe the black holes throw out stars and lose angular momentum, or they're accreting gas and feeding, which also causes them to lose angular momentum. But this is something that's not fully understood yet. We don't know how black holes get this close when they're this big. So that's something that we're still looking into. And what about the Milky Way? I've talked about these mergers. I know I'm worried too, but the Milky Way is actually heading for a merger with Andromeda, our closest neighbor. Andromeda is about 2.5 million light years away in present day terms, but it is moving closer to us. So here you can see there's us, that's Andromeda, and this is a dwarf galaxy called the Triangulum Galaxy. So in the next approximately 4 billion years, the Andromeda and Milky Way will be close enough to initiate a merger. And so here it comes. And that's the beginning of the merger, but they kind of swing and dance around each other until they get close enough where their cores actually end up merging. And you can see that the colors of these actually change in the simulation. That's probably because of all the new stars that are forming. And so some of this gas, and now you can see we've kind of entered an elliptical galaxy formation, as Sarah mentioned. This new merged galaxy is actually referred to by the very, very intuitive name Milkdromeda. I didn't name it, but yeah, so this is the fate of our galaxy in the next 4 to 8 billion years. So now that we've talked about the evolution, formation of galaxies, some of their properties, shapes, and types, let's talk about how galaxies die, which they can in a sense. As galaxies slow down star formation, as I mentioned, they can lose mass due to their black holes or from mergers, as Sarah mentioned. Sometimes enough gas is removed that the galaxy cannot form any more new stars. They become redder as older stars remain, and all the younger blue stars end up dying out pretty quick. So you get these red galaxies, and JWST has managed to find some that are surprisingly far away and formed very early in the universe. So one example is this galaxy right here, JDs, and it was actually formed around 700 million years after the Big Bang, which is quite a short period of time after the Big Bang, comparing it to the 14 billion years that it's taken for us to be here. But this galaxy probably had a very rapid star formation rate, and then it completely shut down eventually. So this is now a dead galaxy. Here's another example of a galaxy that's 10 billion light years away that's also dead. And this is a galaxy called ZF Cosmos, and it's also dead at this point, and it formed 1.6 billion years after the Big Bang. So we are pretty surprised that this early on in the universe, we're seeing galaxies that ended up dying. They must have had very, very rapid star formation, which ended up using all the possible fuel the galaxy had. And sometimes these dead galaxies can actually merge, triggering star formation, and they're called zombie galaxies because you have these dead galaxies coming back once they merge with each other. So what happens, what is going to happen to all the galaxies at the end in the very, very far future of the universe? Well, considering that space is expanding and it's accelerating in its expansion, we don't expect it to slow down. It'll actually speed up. So what happens is that galaxies start getting farther and farther apart. And as galaxies use up all their fuel, all that's left are the dead remains of stars, such as white dwarfs, neutron stars, and black holes. And white dwarfs and neutron stars are like the cores of dead stars, and they contain what we call degenerate matter, where at the lowest quantum scale, all the particles are packed so tight that there's nowhere to go other than a complete collapse. So once all that's left is in here, the age of starlight slowly ends, and these galaxies are filled with just corpses, basically, black holes and all these dead stars. And this is the age, the degenerate era, and this will be the fate of the universe unless we have new theories that show us that maybe there's a more hopeful, brighter future. But that's what we think will happen at this point. But till then, this is going to happen in a few 100 trillion years, so enjoy the age of starlight while it still lasts. Here's an image of the Hubble Deep Field, and you can see these effects that Kumar showed you, this warping of light due to the presence of very massive galaxies in front. And so the light from behind these bright dots is actually getting bent by the gravity. And this is called lensing, gravitational lensing. So that's how you get all these wonky looking weird images. But that's our talk for now. Thank you so much. And our next talk will actually be from UW-Madison right here on October 26th. Yeah. Thank you.